So in the last video I mentioned that some of these vellum constraints only make sense when you are setting them or animating them dynamically. That means while we are running a simulation. What I want to do in this video is give you 4 short examples of how useful that can be. And let's start with inflating a balloon or a toy. So let's drop down a torus, dive in there, and let's increase the rows and columns, and also dial down the radius, something like this. Copy this, and again, let's scale this back a bit further, move it down and to the side so we have some collision geometry. Let's use the vellum balloon preset, which is a combination of cloth and pressure, wire in our geometry and our collider, and then append a vellum solver. Like so. Within the vellum solver, what I want to do is enable the ground plane and then move it down to say -2, like this. And just to make sure we set up everything correctly, let's hit play. And that to me seems a bit too squishy, so let's reset this, and within the vellum cloth here, let's dial up the cloth stiffness to say 3200 and resimulate again. That looks a tiny bit better. So let's stick with that. And what I want to do now for inflating this balloon or this torus, I want to animate the pressure here. And let's just drop down a null, append this to our constraints, and then, while highlighting this null, head into the geo spreadsheet, and let's isolate the pressure constraint here, which is this single constraint. And on the arrest length, it saves the volume of our geometry, in this case 1.22 something. And I want to scale this up at a certain point. So in order to do that, when middle mousing on this null here, you can see I've only got 2 groups, the bend and the stretch constraints. And what pressure is doing, sadly, it's writing this volume constraint into the stretch group too. So if I'd animate the stretch group, I would not only animate the pressure constraint, but also the cloth constraint, which is something I do not want. So instead I will check the output group here and call this one pressure stretch. Like this. And when I middle mouse on the null now, I can see 3 groups: bend, pressure stretch, and stretch. And I only want to animate this group here. So let's do that by finally diving into the vellum solver. And when you dive in here, you can see by this path, we dove in a few layers deep. So basically what the vellum solver in SOPs is, it's an encapsulated DOP-net. And when diving in here, we dive into a particular area of that DOP-net, which allows us to update forces and update constraints in here. And I want to do that with the vellum constraints property node here, which I'll just wire in the force output here, and then I will check the group. So I only work on the pressure stretch constraint here. So none of these constraints is checked here, so when I hit play, nothing should have changed. Which basically is what we're seeing. And we also see that by frame 48, 49, this torus is on the floor, so let's start inflating it from here. So as I mentioned, the volume is stored as the rest length attribute on my pressure constraint. So let's scale that up by checking rest length scale here and setting a keyframe at frame 48. So the scale here is 1, and then moving on to frame 72, and maybe let's scale it by a factor of 3, like this. Reset this and simulate it. And you can see from frame 48 on, it inflates. And this is how you'd animate basic pressure. You might also get the idea to directly animate the rest length, which you definitely could do. You just have to make sure that you are starting with the correct rest length. For example, this is always set to 1 by default. However, the volume that is stored on the pressure constraint in our case would be 1.22. So you'd have to accommodate for that. What I like to do is animate the scale. That works fine for me. So let's go back to the OBJ level, reset this and maybe save it. And let's do another one. This time releasing a piece of cloth at a given point in time. So let's drop down a grid, disable this one, dive into the grid, and let's scale this back to be 2 by 2 and have 50 by 50 rows and columns like so, which is our standard piece of cloth. Again, maybe a torus or some other geo, just as a collider for good measure. And then let's drop down the vellum configure cloth, pipe in our grid and our torus, and then append our vellum solver. In the solver, again, let's check the ground position, move that to -2, and just hit play to simulate this, which is behaving exactly as we'd expect it. So let's say we want to release this cloth at some random frame, 24 for example. What we'll need for that is some constraints that keep it in place. And in our example, we're going to use, again, the vellum constraint, wire this after our cloth, and set it to pin to target, that is. And I like to set the pin type to soft, and as long as the stiffness is set really high, it will just stick that cloth to its original position. And if I set that stiffness to 0, this cloth will get released. So I could be tempted now to just animate this here, and let's try it. Go to frame 23, set a keyframe here, one frame further, set this one to 0, keyframe it, reset the simulation, hit play. And nothing is happening here, because the Vellum solver is not automatically updating those constraints that are animated outside of the solver network here. So let's reset this, get rid of the keyframes by Control-Shift clicking in here, and instead, let's dive into the Vellum solver. Again, drop down a Vellum constraint property, wire this in here, and I want to set this again to a certain group. And as you can see, again, I only got my bend and stretch group. So again, up one level, and in the pin constraint, let's check the output group and call this one pin stretch. So now back into my solver here, and within the Vellum constraint property, I now can check my pin stretch constraints here. And what I want to do at frame 24, I want to set its stiffness to 0. So instead of animating this from a really high value, like 1 billion, down to 0, what I'll do is I will just activate this whole node here only at frame 24. Set the activation to 0. Go to frame 23, set a keyframe here, go one frame ahead, and again set this one to 1, and keyframe it again. Now let's reset the simulation and hit play. And you can see this is behaving exactly as we're expecting, releasing the cloth at frame 24 by just activating this node here at this frame. So that's another way how you can animate or switch constraint, by just activating this node where you dial in the settings for the respective constraints. Again, keep in mind that you have to put them in a separate group if you don't want to influence your whole set of constraints. So back on our OBJ level, let's just reset this thing, copy our grid, disable this one here, and in here, what I want to do is, now, if we run the simulation, and let's just get rid of the pin constraint, and within the Vellum solver, let's get rid of the constraint properties here. So if I run this as a standard simulation, you can see the cloth slips from this collider here, which is expected. But what if I want to stick it to this collision geometry? Well, then we need to dynamically generate constraints. And luckily we can do this in the Vellum solver here by dropping down a Vellum constraint, wiring this in the force output. So you can see the force output is named a bit misleadingly. It accepts many things, not only forces. Within this constraint sub here, let's set the constraint type to attach to geometry. And we've talked about this. We can use this to stick geometry to collider geometry that's close to our simulated geometry. Let's just set the target path to our torus here. And down here, let's check max distance and set the maximum search distance within which the geometry should look for geometry to stick to 0.05. Like this. And when we hit play now, it's still behaving the same. And that is because yet our constraints node is set up to only check those constraints on the first frame. So let's change that to check it each frame. Reset our simulation, hit play again. And we can see now, when the cloth hits that torus, it sticks to it, it's glued to it. So in here, within the Vellum solver, you can work with those constraint nodes that you know from SOP level, but execute them each frame, which is really powerful. Back on our OBJ level, reset to 0, and again let's copy this another time and create our final example here, where we want to stick simulation geometry to each other. Disable this one and dive in here, and let me set this up a bit differently. So what I want to do is, let's take this torus here, move it up a bit and toward the side, and this grid here, let's pin one edge of it. So let's select a few points here. Put this one in a group, let's call it pin, and also create another group, primitives, let's call this one cloth, so this contains the cloth geometry, copy this group, this time call it torus, so it contains the torus. Also what I want to do is in my cloth constraint here, first let's set the group to cloth only, so this is only affecting this grid here, and then let's pin a few points which are in the pin group here. So when we hit play now, only the cloth is falling down and is being held at those points here, which is good. However, I also want my torus to be a dynamic object. So instead of doing this, let's cut those here and merge both of our geos, the cloth and the torus, and wire this in our constraints here, and set up a soft body for our torus here. So I'll wire this in after I configure the cloth, and within those two constraints here, I will set their groups to be only affecting the torus, like so. Like this. When we hit play now, and let's dive in the Vellum solver and just get rid of the Vellum constraints here. So when we hit play now, we can see both of them are simulated and both of them have a different behavior. The cloth being a cloth and the torus being a soft body. I'd like to give this torus here a bit of an initial velocity so it moves over this direction, and that is in -x direction. So let's drop down a pointer angle after the torus, and in here let's create a velocity attribute. It's a vector called v, and let's set it to be -3 along the x-axis. Let's hit play now, and we can see torus moves over, touches the cloth, then falls down. So what you can do with Vellum is write initial attributes like velocity or force onto your geometry that is being simulated, and Vellum will automatically take this into account. However, what I want to do is I want those pieces to stick together as soon as the torus hits this cloth here, which can be done within the Vellum solver with another constraint. Again, wire this in the force output, and we want to evaluate this each frame, and we want to have a glue constraint now, which is used to stick together different pieces of a simulation. I want to stick my torus to my cloth, and down here within the glue search radius, I can dial back the maximum distance a bit to 0.05 in our case. Let's hit play again. And you can see now the torus is sticking to my cloth. And a torus sticking to a cloth might not be the most practical example, admittedly, it's just an easy and quick one. However, you could, for example, use this to stick stuff to spider webs, or have some sci-fi goo that sticks to, I don't know, a robot or a wall of a UFO or something. Stuff like that. So that was a short intro, a short overview of what can be done when you're setting and animating and creating constraints while you're simulating dynamically. And also you saw that the Vellum subsolver is in essence nothing but an encapsulated DOP net. And we're going to have a closer look at this DOP net in our next tutorial. See you then.